Consider the initial value problem. Y prime is equals to minus 20y plus 7 exponent of minus t over 2 subject to the initial condition y naught is equals to 5. I'm going to use Euler's method with a step size of h equals to 0.01 to approximate y at 0.02. And then I'll go on and calculate the absolute error of this numerical method. So we are given that first order ODE. So I'll start by looking at the first question here using Euler's method. When you are using Euler's method, we are looking at ODEs, which are of the form the derivative of y with respect to t is equals to f of ty subject to the initial condition y at t naught is equals to y naught. And for the approximation using Euler's method, we'll get that yn plus 1 is equals to yn plus h of f of tn yn. Now, if we compare these two equations here, we see that our f there is equals to minus 20y plus 7 exponent of minus t over 2, because we looked at what is on the right hand side there of the derivative. And our initial condition, we are saying y naught is equals to 5. That is the value of y when t is equals to 0. So when we substitute this f into this formula here, what we would then have there is yn plus 1 is equals to yn plus h multiplied by minus 20 yn plus 7 exponent of minus tn divided by 2. So I can just go on and illustrate what I'm saying here on a number line. We are starting at t equals to 0. So we are at 0. Then we are moving with a step size of h equals to 0.01. So when you move for the first time, we go to 0.01. Then when you move for the second step again, our step size is 0.01. So we are adding 0.01 to this 0.01 so that we go to 0.02. So what we'll be having there is we are starting at y naught and then go on to y1 and then go on to y2. So for y1, we substitute n equals to 0 in this equation. Then we have y1 is equals to y naught plus h multiplied by minus 20y naught plus 7 exponent of minus t naught divided by 2. Because we are substituting wherever we have n, we put a 0. Then for y2, we substitute n equals to 1 here, so that we have y2 is equals to y1 plus h multiplied by minus 20y1 plus 7 exponent of minus t1 divided by 2. So what we have here are the two equations that will help us obtain y1 and y2. So for y1, we substitute the value of h. We said it's a 0.01, and the value of t naught, we are starting at t equals to 0, so we substitute 0 wherever we have the t naught. And the y naught, we are saying, is this 5 here. So we have that y1 is equals to 5 plus 0.01 multiplied by minus 20 times 5 plus 7, and that will give us 4.07. So that is our y1. We then go on and use this value of y1 to obtain our y2, because we have a y1 here. Substitute the value of the h, the 0.01, t1 now. We are at this point. So we have that our y2 is equals to 4.07 plus 0.01 multiplied by minus 20 times 4.07 plus 7 times exponent of minus 0.01 divided by 2. And the solution that we'll get there is approximately 3.3257. So what we are saying there is the value of y at t equals to 0.02 is 3.3257. So that's the approximate solution of the ODE using Euler's method. We now move on to question number 2 there, the absolute error. For the absolute error, if you still recall, is the absolute value of the difference between the true value and the approximate value. The approximate value is the one that we have just obtained, and for the true value, we need to find the analytic solution of this ODE, of which for the analytic solution, we see that this is a first order ODE. It's a linear first order ODE. So we can solve this by using an integrating factor. But for us to do that, we can just rewrite the equation, put this minus 20y on the left-hand side, and then we would have y prime plus 20y is equals to 7 exponent of minus t over 2. And when it is in this form now, we can see that our integrating factor will be equals to exponent of 20t. So def mu is equals to exponent of 20t. And when solving an equation by using an integrating factor, we multiply throughout by the integrating factor. And then what we would then obtain for the y is equals to 14 over 39 exponent of minus t over 2 plus a constant a multiplied by exponent of minus 20t. So what we have here is the general solution. I have skipped some parts there just because we looked at integrating factors in detail previously. For us to get the value of this constant, we use the initial condition here. So substitute t equals to 0 in this equation, and we are saying the y will be 5. So when you solve that, we would get that our a there is 181 over 39. So we would have y is equals to 14 over 39 multiplied by exponent of minus t over 2 plus 181 divided by 39 multiplied by exponent of minus 20t. So this is our analytic solution. And for the value of the analytic solution at t equals to 0.02, we would have y at t equals 0.02 is equals to 14 divided by 39 multiplied by exponent of minus 0.02 divided by 2 plus 181 over 39 multiplied by exponent of minus 20 times 0.02. That will give us the value of y at t equals to 0.02, and it's approximately equals to 3.4664. So for our absolute error, it's the absolute value of the true value minus the approximate value, and that will be the analytic solution that we've just obtained, then minus our approximate solution 3.3257, and that will give us a value which is approximately equals to 0.1407. So what we have there is our absolute error.